All right, hello everyone. We've wrapped up officially the physics portion of the class. The next unit that we will be discussing will concern chemistry as the physical science of focus. And specifically in this lecture, we will be covering chapters 8 and 9 of the textbook that I did not assign, and that will concern atoms and bonding. To get our feet wet with chemistry, we are first going to do essentially a history of the field dating back to the ancient Greeks. And these were the first people to establish a written record of some sort of thought as to what chemistry is. Okay, and in a nutshell, you can think of the field of chemistry as, what is matter and how does it change? How does it react? What are its properties? Okay. And according to the ancient Greeks, the prevailing argument for a long time was that matter was continuously and infinitely divisible, all right? Which is to say, if you had the ocean, which was filled with water, that's a type of matter, and you took a cup from that ocean, you would have a cup of ocean water. And if you took a smaller cup, you can get a smaller cup of ocean water, and you could keep on doing that so long as you could come up with smaller and smaller cups. It actually wasn't until a philosopher by the name of Democritus, I believe he also invented democracy, hence his name. But aside from politics, he liked to think about the sciences, and he was the one to come up with this concept of atoms, okay? And the Democritus model stated that matter was not infinitely divisible. It got to a point where every substance was composed of, frankly, little balls that were unique to each substance. So if you kept on taking smaller and smaller cups of ocean water, you would eventually get, according to Democritus, one ball of, ocean water atom, okay? And that was actually considered to be a little bit scandalous at the time, but people actually eventually just accepted it on faith, and that was the predominant theory for quite some time. Yeah, so the Democritus model was, and I hate calling it really a model or a theory because frankly it was just a hunch. That went pretty uncontested from ancient Greece up until, the 1800s. And it was John Dalton who was the first person to apply that concept of atoms to the field of chemistry. Up until that point, it was referred to as alchemy, which is really more like bad sorcery than a real science, frankly. And what John Dalton did was he modified Democritus's theory of matter consists of little indivisible balls called atoms, and he was the one that said that okay, there's actually elements involved. It's not that each kind of matter has its own ball. It's that matter is composed of elements, and each element is going to have a different kind of atom, and most importantly, each element is going to have a different relevant weight to it. Okay, and so this is an excerpt from, I believe, his notebook or something, and he discovered, that zinc was an element, and he gave it a relative weight of 56, element units, whatever that may be. And oxygen, he assigned that a relative weight of 7. Okay, this is a very crude table, but yes, zinc as an element is more massive than the oxygen element. Okay, so he's really the one that started to refine the nuance of the different subcomponents of what matter is. All right. There's also 5 rules that I would like you to know that comprise Dalton's theory of the atom or his model of the atom. Okay, and I'll try to write them out over here. The first one, and this is actually not novel to him, is that all matter is indivisible, or rather, it is composed of indivisible atoms. So we haven't abandoned that part quite yet. See. And again, the next part, one element, of any given element is composed of identical atoms. Three, just to rehash what I said before, different elements will have different masses. I'm running out of room. We're going to slip 4 all the way up here. This is where we get into the concept of chemical bonding. Chemical compounds, and a compound is anything, a substance made of many elements, like carbon dioxide is carbon and oxygen. Compounds have specific ratios of elements. This was a big discovery. He found that if he took, one equivalent of carbon and 2 equivalents of oxygen and reacted them together, he would always get, 1 equivalent of carbon dioxide, 2 oxygens for every carbon. 5, atoms aren't created or destroyed. And the fun thing about this is that pretty much everything except 4 and 3 were disproven by later models. The next scientist to further refine the model of the atom was J.J. Thomson. This was also in the 1800s, okay? So we are rapidly advancing the field at this rate. And he did this with something called the cathode ray experiment, which is pretty cool and basically the basis of how old TVs used to work. So how did that experiment, how was that set up, and what did he discover about the atom? Well, if you take 2 metal plates and you put them in a vacuum tube, and then you hooked up that vacuum tube to a power source, remember our circuitry lecture from last class, once you turn on that high voltage source, he actually observed a glowing ray come out of what's known as the cathode plates. And what this was doing is it was pumping out a negative charge. And this was really fascinating because no matter what kind of element metal you put in the cathode, let's say it was iron, let's say it was zinc, let's say it was whatever, the same glowing ray with the same negative charge would flow out. It was this beautiful like purple charge beam, okay? And it turns out that these rays are electrons, which, as you know, are incredibly small, and they have a negative charge, and most importantly, they are in everything. And since the metal plate before the experiment happened was neutral, that means if a neutral substance exuded a negative charge, whatever was left behind must be an equal but opposite positive charge, okay? So now we are starting to deconstruct this notion that, frankly, atoms are indivisible. So we've now added some crucial caveats or addendums to this to the Democritus model, which then became the Dalton model. And namely, what those modifications are is 1, atoms are divisible. By hooking it up, an element up to a circuit, you can have it eject out parts of it, okay? So not so indivisible, it would seem. The second thing that we've learned from the cathode ray experiment is that an atom is composed of negative subatomic bits or parts. And these are electrons, okay? And presumably positive bits too. And we now know this as protons. But this is a bit of a hand wave, okay? We didn't detect any positively charged material. You know, he knew these cathode rays were negative because he put a negative test charge by the tube and it deflected away because of Coulomb's law, okay? Similar charges will repel. We don't know for sure by observation that we left behind a positive charge. That's purely inference. And so, well, where is that positive charge exactly? So Thomson just made a guess, the best guess he could with the evidence that he had. And he said that an atom is going to be basically a ball of positive charge, okay? So we're still thinking of atoms as balls. And inside, there's a random distribution of these negatively charged subcomponents that are much more easily removed by an external force, okay? And so the moniker that he has for this it's called the Thomson model, but it's more lovingly referred to as the plum pudding model. And so all these guys, I think, were British, except for Democritus, he was Greek. And plum pudding, it's kind of it's like pudding isn't like pudding as Americans know it. It's like a fruit cake. And so he viewed it as this pudding, which is really a cake, that has like these little chopped up plum bits scattered in about randomly, stuck in a positive matrix. Negative plum, chopped plums scattered into a positive cake, if you will. And believe it or not, people did not super accept this. They were like, yeah, okay, there's charges in here in a neutral atom, it's divisible, but just throwing them in like a cake seems a little sloppy. Yeah, there were many scientists. I think a lot of scientists in Japan were very critical of that idea because when they discovered that you really can't have, or they noted that positive and negative charge doesn't commingle in space like that. It just breaks the laws of physics, and I'm not going to get into that here. But what happened in 1907 was a very rigorous follow-up that did a good job refining what what we derived from the Thomson model, the fact that there's subatomic components to an atom. And Ernest Rutherford and Geiger did this experiment, and I believe they were actually mathematicians or physicists. Actually, they were more math guys. And what they did was they thought of Coulomb's law, you know, everyone's favorite law in this class. They realized that an intense concentrated charge should exert a strong electrostatic force. And Geiger, I think I said, like he's the guy that invented the Geiger counter for like radiation. He discovered something called alpha radiation, and these are alpha radiation is like uranium. They're going to emit alpha particles, which are basically the nuclei of helium atoms. They're very positive, okay? And he got the idea to use that to test exactly what the picture of the atom truly is, okay? So Rutherford applied Coulomb's law, and he calculated that the negative charges, according to this plum pudding model, were too spread out to exert any meaningful force that could deflect a very positive charge flying through it, like an alpha particle, okay? So he set out to refute the plum pudding model by making a very thin but very dense sheet of atoms using a gold foil. And it was 60 nanometers thick, which was actually thinner than a piece of human hair, and you could pretty much see through it. And he made this by taking a block of gold and just hammering it out as far as thinly as he could. All right, so he basically made like, you know, a single wall of atoms here. And he was going to see, okay, how does this wall of atoms respond to charges being flung at it? Over here, this is the gold foil. We have a radiation source put into a lead container. So this is shielding. And that radiation source is going to shoot out a beam of positive charges of radioactivity at this gold sheet, all right? Like a gun. And Rutherford predicted that a layer of atoms this thin in this gold sheet wouldn't be able to stop that giant positively charged alpha particle beam. It would fly right through, and you can't see radiation directly. So to visualize where it went, he surrounded this gold sheet by a fluorescent screen. And he predicted that all of the beams would go right through the gold foil, you know, like phasing, and it would stain the fluorescent sheet and generate an image, like it would paint this area black, basically. And he thought that that these negative charges like this, they wouldn't be able to influence a fast-moving positive charge going through. Now, if the negative charges were in a very significant arrangement, then they could deflect the positive charge, and you would expect to see radiation hit and stain the fluorescent screen elsewhere, completely randomly. And what happened was really cool. It was none of those things. Most of the particles, and I'm going to say, I believe it was, you know, more than 99.99% went through the foil from the radioactive source and hit directly behind the screen. And it's and it marked it over here. And it didn't damage the foil. It didn't punch a hole through. It's just like it went through a wall, okay? However, about 1 in 20,000 of those particles did scatter, and they scattered quite dramatically. They would reflect at really extreme angles, sometimes so extreme they bounced basically right back where they came from. And according to Rutherford's initial predictions, that was mathematically impossible, okay? Because he thought an atom, a single wall of atoms, wouldn't be able to provide enough back force. It's like firing a cannonball at a piece of paper and having the cannonball bounce back right at you. That was disturbing. So after many sleepless nights, he eventually concluded that the atom was mostly empty space. That is the only reason why more than 99% of the radiation went through without destroying the foil. So if it wasn't pure empty space, it would have the cannonball would have gone through the piece of paper and left a hole through it. All right. However, how do we explain for the 1 in 20,000 alpha particles that got bounced wildly off course? Well, the only rationale for that is that the atom, even though it was 99.9% empty space, the middle of it must have been very, very small, very, very dense, and very, very positively charged. Because remember, the alpha particle is positively charged, and so that would bounce it. And if you got a direct hit, it would, boom, come right back at you. And so the word for this, by the way, he decided to call this the nucleus. So we've made some really big advances in the model of the atom by using, pretty not fancy equipment. No, like super expensive atomic microscopes were used here. It was just a block of uranium, gold, and some material that would glow when it got hit by radioactivity. But look what we learned. The middle of the middle of the atom is mostly positively charged, which means we know there are negative electrons in the atom. They must be floating around somewhere outside, all right? So we've made quite the leap from the Thomson model by doing one simple experiment. I think this is one of the coolest things chemists have done. And not only is this discovery of the nucleus and the electron cloud outside of it incredibly cool, but discovering the nucleus tied up a lot of loose ends in chemistry up until that point, okay? Let's realize that the major thing that distinguishes one element from the other is the number of protons in the nucleus, okay? I think I talked about this during the heat lecture briefly, but I'm going to recap for you that, remember, the hydrogen atom has 1 proton, so its atomic number is 1. The helium atom, or all helium elements, whatever, has 2 protons in its nucleus, so its atomic number is 2. Lithium, the third element, has 3 protons in its nucleus, and so forth. Now there's a reason why elements are different, and it really comes down to their nucleus, not so much their electrons. Furthermore, we eventually discovered that in addition to protons, a nucleus also has the neutral neutrons, and these were much harder to discover because they don't really interact with things. And the number of the nucleus doesn't impact the number of the neutrons in the nucleus, doesn't impact the chemical identity of the element, but having too many or too few neutrons in a nucleus will make that element unstable, or that nucleus unstable, which means it will be radioactive, okay? So collectively, the term for the umbrella for protons and neutrons, that is called a nucleon. That's a word that you should know. Let me define that for you. So a nucleon, that's a proton or a neutron, basically. Or neutron. Okay? And in a given element, the number of neutrons will actually vary, okay? And here's an example. 99.9% of all hydrogen atoms exist as hydrogen 1, okay? And that means it has 1 nucleon, which is a proton, and no neutrons in its nucleus. Hydrogen 2 composes, I think, 0.1% of all hydrogen in the universe, or maybe it's 1%, I don't know. The important thing is to know that the difference between hydrogen 1 and hydrogen 2 is that this has 2 nucleons in its nucleus, 1 proton and 1 neutron. If it had 2 protons and no neutrons, then it would be helium, a different substance, a different element altogether. But there's no chemical difference between these 2 nuclei, but there is slightly different properties. They have different, densities or masses, what have you, between the 2. Okay. And what's really rare, but still, in the universe, is hydrogen 3. And this is where we get to see instability come into play. There's 1 proton in the hydrogen 3 nucleus for every 2 neutrons, okay? And think of it this way. It's kind of like, carrying too many shopping bags in your arms. When you get a lot of neutrons in a nucleus, it has a tendency to fall apart. And that is essentially the basis of radioactivity. So hydrogen 3 is actually a radioactive version of the hydrogen element. And the word for different elements, the same element but different number of nucleons, that's called an isotope. And so you maybe heard that term before. Hydrogen-3, or also known as tritium, is a radioactive isotope. And if you ever wondered if you've encountered this before, you have. And those red exit signs by like fire escapes and stuff, they're glowing red because they're actually filled with compounds that contain tritium. And when things sometimes glow when they're radioactive, you know, that exit sign isn't hooked up to a power source because you want to be able to see it if the lights are out while there is a fire. Okay, so even though it's very rare, you've certainly encountered this before. Now, the last thing I want to discuss about, you know, nuclei is this notation over here. This can be a little bit, I think, confusing to the uninitiated, and I want you to be aware of two forms of notation. One is called the mass number. This refers to the number of nucleons in a given element. The elemental symbol for hydrogen is H. And there's also the atomic number, and this is specifically the number of protons in that atom of element. So for this hydrogen atom, chemical symbol is H, it's going to have an atomic number of 1. It's always going to have an atomic number of 1 because all hydrogens have 1 proton in their nucleus. But this isotope is going to be, it's going to have a 1 as the mass number because it also only has 1 nucleon in its nucleus. Compared to hydrogen-2, well, that has 1 proton and 1 neutron. 1 plus 1 is 2. So in the superscript position, the mass number is going to be 2. The atomic number is still 1, okay? If you ever want to find out how many neutrons are in something, a certain isotope rather, you take the mass number, you subtract the atomic number, 3 minus 1 is 2. That means hydrogen-3 is going to have 2 neutrons in its nucleus. Okay, there's a lot going on in this slide, but let's quickly recap what we've learned so far from the Rutherford model of the atom. First, we know that the atom is mostly empty space. Second, most of the atom's mass is concentrated in a very small, very positively charged nucleus in the center of it, okay? And third, in the vast amount of empty space around that nucleus of that atom, there are negatively charged electrons somewhere, okay? An equivalent number of electrons to protons. Somewhere is not a very satisfying depiction of the electron's location. So our goal now is to discover the structure of these electrons, or their arrangements, okay? Are they rotating about the nucleus in specific orbits, or are they flying randomly about in a diffuse cloud? So, or something else, you know, like what is it? Well, to answer these questions, the next key set of experiments that were done were the atomic emission experiments. What scientists would do in these experiments is they would fill up an empty glass tube with a pure element, usually a gas, like hydrogen gas, and then they would zap it, kind of like that cathode ray experiment that Thomson did, except here there's no cathode-anode plates, there's no circuits, so the energy that you pump into that element sample, it has like no escape, or it's not making, you know, a loop in the way that the Thomson experiment worked. Once you energize that sample in that tube, it needs to eventually release that energy in some form, and it does so by actually emitting light as opposed to a cathode ray. Strangely, each element will only emit very specific colors or wavelengths of lights, depending on what the element is. You know, let's take a look over here This graphic contains atomic emission spectra of hydrogen, helium, mercury, and uranium, actually. And let's just for now only focus on hydrogen, okay? Oops. I'm going to circle that here. Ignore these. I actually clipped off uranium. It was too busy, I suppose. All right. Excuse me. So let's look at the hydrogen emission spectrum. What's going on here? Well, we've zapped a whole bunch of hydrogen, and the energy that it released, I said, was light. But it's not white light. It's not random light. It's actually only specific wavelengths and colors of light. Specifically, this shade of red, this wavelength of yellow or orange, these shades of blue and purple, okay? What does that mean, though? You know, it's pretty, but like, what do these pretty colors have to do with the electrons, okay? Well, we know from the Thomson experiments, the plum pudding one, the cathode ray tube experiment, that electrons move when you zap them, okay? But here they only move in increments because we haven't established a cathode ray tube with a specific path for the electrons to follow. So let's just pretend that, you know, this is the nucleus in this little cartoon that we got. And let's pretend, I don't know, that we've got like an electron over here. Let me get my pen. Oops. Let's get a pen. And let's draw an electron. Oops. Over here. And remember, electrons are negative and the nucleus is positive. Okay? So remember, from Coulomb's law, we all love Coulomb's law, positive charges and negative charges are attracted to each other. Okay? When we pump this electron full of energy, okay, what's going to happen is we are going to push that electron away from the nucleus. Okay? So it's going to hop a certain distance higher, at a higher energy level. Let's say we're going to put the electron over here. Okay? Like, think of a rubber band. When we put energy in, we increase the distance of like one side of the loop to the other side of the loop. Okay? We pull things that are attracted to each other apart. That is a higher energy state. All right? But it's not going to stay there forever. Just like how when we heat a pot on the stove and the stove radiates its heat and cools down over time, that electron is going to radiate the energy it now has, the extra energy, but it's going to release that energy in the form of light, specifically a photon, which is like a packet of light. So we're going to draw an arrow down showing it dropping back to rest, and in order to do that, it has to release the energy that came in. But we've converted it from, like, you know, the energy from the zap, and now it's light, okay? So it is a specific color moving from here to here, okay? Let's take a look again at the emission spectra. Going from here to here, this seems to correspond to an emitted wavelength of around 410 nanometers, okay? Doesn't exactly match up over here, but it's close enough for our purposes. That's a pretty high, that's a pretty short wavelength, a pretty high frequency or energy light, so that's going to be, you know, purple, okay? And that makes sense because falling from here to here is going to correspond to a rather big loss of absorbed energy. However, if the electron only absorbed a little bit of energy and went up to here, it would fall back down a smaller distance to rest, and it would correspond to a smaller amount of energy that was released, and that would be, you know, more red. What we've discovered here is that electrons are occupying specific, discrete, stepwise levels of energy. Another word for this is called quantized. And every element seen here has different quanta of energy levels. Saying that again in plain English, by simply zapping an element and causing and counting the colors that it fluoresces, we can learn that the electron will only exist at certain distances from the nucleus. If this was random and that an electron could absorb any amount of light of energy and release any amount of energy completely randomly, then the amount of energy that would be released would also be random, which means the wavelength of the light would be random, or the frequency, which is to say the color. Instead of lines, we would get the rainbow as a spectrum, but we don't see that. It was Niels Bohr who took these data and refined the Rutherford model with it further. It was Niels Bohr who realized that because electrons absorb energy and release it at specific frequencies, then these electrons can only possess specific energies. And I'm going to repeat some of the points from the last slide here just because it's subtle, but it's really important, and I know this can be hard for students to understand. I'm going to repeat that, if we've got a negative electron that is, like this far from the nucleus, from the positive nucleus, it is going to have a lower energy than one that is farther away from it, okay? Because we are pulling apart two things that want to be together, the positive and negative charge. And the act of that requires energy. That's why we say it's at a higher energy level. Specifically, it is kinetic energy, the energy of motion, that's causing it to change position like that, the electron. So, an electron at rest is constantly moving about the nucleus at a constant energy. And since the energy isn't changing, that means the distance between the positive nucleus and the negative electron also needs to be at a fixed distance. That's kind of like an orbit when you think about it, okay? The Earth, give or take, is always going to be a certain distance from the sun. I'm going to reiterate here, though, that gravity is not holding the electrons to the nucleus. It is electrostatics or electromagnetic attraction. But the reason why electrons aren't, glued to the surface to the nucleus is largely due to its inherent kinetic energy and other things. The electrons want to move, so it's going to fluctuate or orbit at a certain distance, basically, corresponding to how much energy it has. If that electron's moving faster, it's going to be also higher out in orbit, okay? And the only thing we can do here to increase the electron from a lower orbit to a higher orbit is to pump it with energy, pump it with strong light, pump or zap the hell out of it. Whatever it takes. But the important thing to know is that once you increase the energy of that electron, it is going to then occupy that higher level. And this is where things get a little bit wild, okay? This is when it moves from this orbit to this orbit, it doesn't just travel outwards. It actually basically teleports, okay? One moment is here, the other moment is over there. And that is very mind-blowing, and it's upsetting to kind of think about. There are some people out there that think this is actually evidence that space itself is quantized. We can only occupy certain parts of the grid of the space-time composing a universe. But that's a discussion for another day. I just thought that was interesting. But, to sum up, as long as that electron is not emitting or absorbing energy, it is going to stay in whatever orbit it is currently in. Think of it like inertia. And when that orbit does change, it always must accompany some form of emission or absorption. If it is going down, it's got to lose that energy in the form of radiation. If it's going up, it needs to absorb. That's what the data says. And if you thought that was complicated, just wait and see. Bohr's model of the atom, which in a nutshell is electrons occupy specific orbits, and changing orbits requires the input or output of some kind of energy. That did not stay out of the trash can for very long. Do you remember that double slit experiment from our last lecture, how light will behave like a particle and like a wave? Okay. It turns out all matter has particle-wave duality. Human beings are also wave-like. It just so happens that when a substance has a lot of mass, and by a lot of mass I mean, maybe proton-sized or bigger, it's not going to be very wave-like. That's why we can't walk through walls so easily, okay? Because we are mostly particle-like in nature. Electrons are very small, though. They do have a very distinct wave-like character to them, okay? Electrons, it's not fair to treat them as particles. Because they have such a wave-like component, you need to treat them as essentially a standing wave. And there's really no easy way to describe that in a class like this. The only thing I can do to break this down for you is to use the word uncertainty. These pictures are called wave functions of the different energy levels of a hydrogen atom, okay? Wherever you see a color, that tells you a probability of where that electron wave will be manifested, okay? So if you look at, this energy level of a hydrogen atom, this ring, it does kind of look like an orbit, okay? So this is where energy levels are coming from, all right? But it doesn't, we're not saying that the electron is a ring rotating around the nucleus. What we're saying is at any given point in time, an electron can be anywhere in these colored regions. All right, and the warmer that color is, the higher probability that electron wave will be present in that zone. And it's kind of wild because some of these shapes, they're kind of psychedelic. Like look at this orbital function over here. An electron could be in two places, at any given moment, which is pretty wild to think of, all right? This isn't two electrons. It's just showing you where they like to hang out at this certain energy level, okay? So I don't want you to really worry too much about the exact nature of what's going on here because I'm going to let you in on a little secret. Nobody understands it, really. The math of understanding where the energies, where the wave function of the electron is, completely falls apart with any atom more complicated than hydrogen, okay? At that point, it's all guesswork. The takeaway here is that electrons do not exist, not orbits. They do not exist in orbits. Rather, they form electron clouds or probability clouds. That's the only thing I want you to take away from this slide, is that at higher energies, the electron can arrange itself into fancier shapes, okay? And that's all right. now that we've had a nice brief tour through the history of the atom, we are going to do some chemistry things to atoms now and learn how to count them, how to do chemical measurements and calculations with them. And one of the most important things, a chemist could do is learn how to count atoms, okay? Well, that's not a difficult thing to do, but it's not as straightforward as you may think because atoms are very, very small. There are more molecules of water or more atoms in those water molecules, more in a cup of water than there are stars in the known universe. That is how small an atom or a compound is. So we need to use a really large unit or a grouping or a reference to describe realistic quantities of atoms that we would use on the day-to-day basis, okay? And the unit for a bunch of atoms that chemists like to use is called the mole, okay? And it's not the cute little creature. It is specifically 6.022 times 10 to the 23 things. So you could have a mole of llamas. That would be an incomprehensible amount of llamas, but a mole is really not going to be used in any context realistically other than to describe very small stuff like an atom. The word mole, by the way, I think comes from this German word. I think it's molecular weight is how we would sort of pronounce it, molecular Gewicht or whatever. And basically, it gives a hint as to how this number was derived. It was derived from the molecular weight of a sample that happened to have had this many atoms in it, okay? So think of it this way. The mole is sort of like the chemist's dozen. I like using that analogy. We say a dozen of eggs, that's 12 eggs. Well, 12 atoms really isn't a lot. 6.022 times 10 to the 23, that is a lot, okay? And I forgot to mention, this I think will help give you a flavor for just how small an atom is. A proton, we actually have measured the mass of a proton. It is 1.66 times 10 to the negative 27 kilograms, okay? So that is a really, really small amount of mass, all right? And another way, if you don't like writing that out, is saying that a one proton equals the weight of that is equal to 1 Dalton, dA, or atomic mass unit. Those are synonyms. Something you should know. So yeah, it doesn't hurt to repeat that a mole is kind of like a dozen. It's just way bigger, okay? If I had a dozen donuts compared to a dozen trucks, what do you think would weigh more? The dozen trucks. Even though I have 12 of each in both hands, because trucks are so massive, 12 of them is going to have a lot more mass and is going to weigh a lot more. The same goes for elements. Elements with a higher atomic number will be more massive because their nuclei are going to have more protons and neutrons in them. Electrons are basically massless, so they don't really count. But this is sort of where that term molecular weight comes from, okay? This is one of the ways we discriminate between one element and the other, the weight of their atoms. Check out this progression in this table. The first element, I've said this before, is hydrogen. It has 1 proton in its nucleus, and it turns out 1 mole of hydrogen gas weighs about a gram, okay? That was kind of, set up that way. Helium has an atomic number of 2. It's got 2 protons in its nucleus for the most part. Its atomic mass is actually 4 grams per mole instead of hydrogen, which is 1 gram per mole. All right? It's a little bit higher because helium has more neutrons in it to help mitigate the proton-proton repulsions in the nucleus. Okay, so it's more massive, but we have a trend of increasing atomic number, increasing atomic mass. Lithium has 3 protons in each of its atoms nuclei because its atomic number is 3, and it's even more massive at 7-ish grams for every mole of lithium. Oxygen, zipping ahead, has 8 protons in its nucleus, and a mole of them, a mole of oxygen elements is going to be 16 grams per mole. And we can do this to compounds as well. Check this out. You know, water, it's not an element, but water consists of 1 oxygen and 2 hydrogens. You know, it's dihydrogen oxide, all right? The atomic mass of oxygen is 16. The atomic mass of hydrogen is 1, and we have 2 of them. 1 plus 1 plus 16 is, lo and behold, 18. So we can get molecular masses for moles of compounds based off of the elements that compose them. And a scientist by the name of Mendeleev discovered that, you know, this trend of increasing atomic number as well as increasing atomic mass, or they called it molecular weight, I guess, in Germany or whatever, even though like hydrogen and like helium isn't a molecule, but whatever, it's an element. Mendeleev also discovered something pretty wild. He discovered that if you arranged the elements in a certain way of listing them, like in a table, he discovered that, I'm going to write this out for you because it's important that you know this. He discovered, here's my pen, that the, come on. This pen is so unresponsive. It's like not drawing. Okay, here we go. The physical and chemical properties of the elements repeat in a periodic way. This is called the periodic law. And this is crazy, okay? He discovered that, for example, helium is an unreactive gas, all right? A few elements down this table, a certain number, he observed another element that also happened to be an unreactive gas, okay? And then a certain number later, he discovered he could predict the repeat of another unreactive gas. So, how can we arrange this table in a way that highlights these periodic properties? So what Mendeleev did was he arranged the elements not in a list, but in a table, where the elements that lined up in a certain row these all had some unifying characteristic. And he determines, what would go next in the series going left to right based off of the molecular weights or the atomic weights, since these are atoms, okay? So what's really cool about this is that, let's look at calcium, for example. Calcium, he knew, had a weight of 40 grams per mole of calcium. The next thing on the list was titanium, and that has a molecular weight of 48. All right. What's really interesting is that he put a gap over here. All right. Nothing on this table has a jump of like more than a few grams per mole. Potassium to calcium only goes up by 1. There's no reason for calcium and titanium to have such a big difference. So the reason why we have a gap here is because he knew that there was an undiscovered element, all right, that had an atomic weight intermediate of calcium and titanium, but would have a property similar to all of these elements, okay? And there are actually many gaps, if you've noticed, in this table, because it took a while to discover all of the naturally occurring elements. But now let's take a look at the table that we know today. Here we have a complete gap-free periodic table, okay? And I'll say it again. The reason why we call it a periodic table is because the elements in each column are going to have something in common. As we traverse down the order of elements as prescribed by their atomic numbers, boron 5, carbon 6, nitrogen 7, we are going to have these properties repeat once we complete a row and start back at the left again. Sodium and lithium are going to have a lot in common. Magnesium and beryllium, they're also going to have a lot in common, okay? And I know the table kind of has these weird jumps in it. Don't worry about the exact rationale as to why. That's not really part of this course too much, but there is a reason, all right? And I'm not gonna show you anything that's an exception, okay? Oops. So before, what I'm going to do in a little bit is tell you exactly what these what the unifying properties are of each column in the periodic table, or each family. But first, I want to do just a little bit, some definitions that I think are important for you to know moving forward. All right. Let's see, let me get the pen ready again. Okay. So the first thing I want you to know is that the term, why does it always do that? The term for a column, there we go. That can be called a family or group. I'm not going to care really too much what you call it. I just need you to be aware of the possibilities. A row can be called a row or a period. Either or. The periodic table, in addition to families and groups of united properties and rows of not similar properties but increasing atomic weight, this periodic table can be further subdivided into groups, okay? These first two groups and these last 1, 2, 3, 4, 5, 6 groups, these together are called the main groups. these are the ones that, these have the most, these are the most periodic of all the groups. These groups are less, I guess, periodic, you could say. These are much easier to study and classify, and they behave very predictably. So these are the ones that we will be talking about the most. Over here, you may have noticed, we've got this like blob in the middle. These are called the transition elements. This is another group in the periodic table. These have really interesting chemistries and really interesting reactivities. There is a rhyme and a reason to how they behave. It's just very complicated. So we're not really going to talk about them. This stretch over here, these two stretches, where? Here. The lanthanides and the actinides, these actually, if you squish them all together, should fit over here between lanthanum and hafnium. And these over here should fit between actinium and rutherfordium, okay? These are called the rare earth elements. The rare earth elements. They are not that rare, actually. They are just actually very hard to purify, and they've got some pretty interesting properties. These have the lanthanides. I've done some research into these. They've got various applications. Neodymium is used in really strong magnets. Europium, samarium, and erbium, I believe, are used as phosphors in your pixel displays. And I could go on. The actinides, a lot of these are unstable. All of these are unstable and radioactive, actually. So you really don't want to be in the same room as any of these. Like, here's plutonium, here's uranium. Those names probably sound familiar to you. And yeah, we're not really going to talk about them ever again. I just want you to be aware of their existence. Okay? I'm going to need some more room here, I think. Some more definitions. Look at this key, all right? A metal is any element that is shown in blue, okay? Some common properties of metals are here we go. They're going to be shiny, hard, conducting, malleable. All right. These are going to be generally some common characteristics. They're usually solid at room temperature. What else? Oh, they also tend to have, well, if they're solid at room temperature, they will likely also have a high boiling point as well. Okay. And I'm speaking broadly here. There are, of course, exceptions. Hydrogen is a little bit of a weirdo. Sometimes it behaves like a metal, sometimes it doesn't. So just forget about that in terms of, you know, these classifications. The opposite of a metal is going to be, as you would imagine, a non-metal. And non-metals are going to usually not be shiny. They're usually soft or liquids or gases at room temperature. And they are usually poor conductors and are not malleable. They're fragile or brittle, okay? So they're all the opposites, and they're not conducting. They're bad conductors of heat, they're bad conductors of electricity, generally. And as you'd imagine from the name, we've got semiconductors, also known as semimetals or metalloids, and they are these green elements over here. And as the name kind of indicates, They're a little bit in the middle. They can sometimes be conducting, sometimes they're shiny, sometimes they're hard. It depends on the circumstances. Silicon is the most famous semiconductor because its semiconducting properties, like I mentioned, I think last lecture, allows it to, that gives it its ability to function in computers. All right, so that's a lot of info. Take your time to just write it down and don't memorize it, but just understand it and know where to reference this information when the test comes. All right, now this is the fun part. Now we're going to begin the tour of the periodic table, specifically the main group only. And we're going to establish what these periodic trends are that I keep yammering about in greater detail. The first group, which I have not grayed out over here, these are called the alkali metals, all right? They consist of lithium, sodium, potassium, rubidium, and cesium. I should note, you do not, no memorizing, okay? I do not want you to memorize, like, oh, K is potassium, okay? I don't care if you know what the elements are. I have to know what the elements are for my job, but you don't. I want you to know what the unifying properties are for each of these things, for each of the alkali metals, okay? So don't panic. I will never ask you, find me rhenium on the periodic table. No, forget about it. So, sorry. I just wanted to remind you that I'm not going to quiz you on the names, but I will quiz you on the properties. So, what are the properties of the alkali metals? With the exception, again, of hydrogen, because hydrogen is weird, the properties of the alkali metals are... Get my pen back. They are reactive. They tarnish in air, and they will explode in water. It's really cool. Google a video of someone chucking a lump of sodium in the water. It's pretty. It's fun. I know I said metals are hard, but this is kind of an exception. Alkali metals are actually soft elements. Okay. You can cut all of these with a spoon. That's how soft they are. What else? They are also all shiny, and they're all. I'm not going to call them silvery because even though they look like silver, they're not silver. So I'm going to call them shiny, just like any metal would be. Okay? Something else I want you to know about them is that every group 1 alkali metal has one reactive electron to it. Okay? Hydrogen only has one electron, all right? Lithium has 3. Sodium, I think, has 11, and so forth. So these are going to have multiple electrons in them, don't get me wrong, but only the outermost electron in that electron cloud can react with things, all right? And it just so happens that all of these alkali metals are going to have one electron that they can react with. That's the only thing you have to know in terms of reactivity. Oops. All right, next up we have group 2. These are the alkaline earth metals. They consist of beryllium, magnesium, calcium, strontium, barium, and radium, okay? And as the name suggests, they've got some similarities to the first column even, okay? They are shiny as well, just like the alkali earth metals. And they are a little reactive. They will tarnish in air slowly, And you throw pure magnesium, pure calcium, whatever in water, and it'll fizz. It's not going to blow up, but it'll react. I said the group 1 metals were soft. These are firmer. These are firmer metals. It is you can't cut these with the spoon. They're not like butter, you know? And in terms of reactivity, they have 2 reactive electrons. 2 reactive electrons in group 2. I wonder if there's going to be a trend here. I'll remind you that we are going to completely bypass the transition metals. You could spend a whole class just discussing these. It's called inorganic chemistry. That's not relevant here. But all you have to know is that these transition metals are going to have very different properties and reactivities compared to everything else and to each other. But the next main group that I want to talk about is the boron group. Boron for B, we're right over here. So yes, I know this is a little confusing. This is the first group, this is the second group, this is the third group. This is not a main group. Ignore this. I can't say it enough. Anyway, the boron group, it consists of the following elements: boron, aluminum, gallium, indium, and thallium. And I'm going to kind of contradict myself. I know the periodic law exists, but they actually don't have all that much in common. They've got some things in common, but not as much unity as the alkali or the alkaline earth metals, okay? They, in general, are not very reactive. Okay? They often, they're rich in semiconductors. That's another kind of periodic property that they have, rich in semiconductors, rich in semis. And they also got a lot of useful tech applications. I believe indium in particular is used a lot in touchscreen devices. And as you'd imagine, the price of indium you can expect will go up as more and more touchscreens are being developed. The last thing I want to tell you about the boron group is the number of reactive electrons they have, their outermost electrons. They have 3 reactive electrons because they are in group 3. Next up is group 4, also known as the carbon group. The carbon group will contain carbon, which I think we're all familiar with, silicon, germanium, tin, and lead. And like the boron group, they're actually pretty diverse and don't have a lot of things in common. It's a mix of metals and non-metals and metalloids. But in general, I would say that they are the least reactive group. Actually, that's a lie. They're the second least reactive group. You'll see why. Of the groups that react, they're the least reactive. There's a group that doesn't react at all that we're going to see soon. And even though they're not very reactive, this seems counterintuitive, but there's a reason, I promise, that we're going to uncover at the end of the lecture. They have 4 reactive electrons. Okay? The number of reactive electrons that an element has does not dictate its reactivity. It has 4 boring electrons, okay, as opposed to 1 hyped up hyper one, okay? All right, group 5. I believe this is pronounced nitrogens. The P is silent. Here we start to see our beloved periodic table make an appearance again. The properties that unify This group, which contains nitrogen, phosphorus, arsenic, antimony, and bismuth, these are going to be overall, we're going to say that they are mildly reactive, you know? They are mildly reactive. And in particular, they do a good job reacting with group 3, group 5 and group 3, okay? They are actually famous for forming really strong compounds with very strong bonds. Nitrogen in particular can form what's called a triple bond, so it's a really strong compound. And altogether, in total, they possess, you guessed it, 5 reactive electrons. Chalcogens are up next, group 6. These consist of some familiar ones like oxygen and sulfur, and maybe some less familiar elements like selenium, tellurium, and polonium, okay? Polonium is radioactive, so I don't think it's not stable. There's not really a lot of it to take pictures of. Some properties of the chalcogens are that they are all pretty reactive nonmetals. All right. With the exception of oxygen, these commonly form very noxious and vile compounds that are rather poisonous. Sulfur compounds, in particular, I'm sure you know, forms these rotten egg smelling compounds that are just awful. There are actually instances when sulfur was kind of first being worked with in like the 1800s, where European chemists would try to, generate sulfur compounds, and they would create a plume of sulfur gas in their lab that would spread out through town and cause mass hysteria, and people would just be minding their own business one day, then just get hit with such an awful smelling chemical, so noxious that they would just throw up right there on the street, vomit, and pass out. Chemists in particular were not well esteemed back in the day. I actually worked quite a bit with sulfur compounds when I was in graduate school, and I had to open the bottle that contained it in a special, like, vacuum sealed box. And if I took the glove that I used to open the bottle with out of the box, instantly the whole room for the next 2 days would be uninhabitable, intolerably stinky, instant headache, gagging. It was awful. Avoid working with these compounds if you can. As you guessed it, they also have 6 reactive electrons. They also like to react with group 2. Isn't that interesting? Group 5 likes to react with group 3. Group 6 likes to react with group 2. I wonder if there's also a common reason for that. The halogens, also known as group 7, consist of fluorine, chlorine, bromine, iodine, and astatine. The unifying properties of this group are that they are all super reactive, nonmetals. They're also quite poisonous and foul-smelling for the most part. I told you sulfur compounds are unpleasant, but fluorine and chlorine gas, these are weapons of mass destruction, actually. In addition to smelling awful, they will kill you quite quickly. Bromine is kind of cool. It's one of the few elements that are liquid at room temperature. It's also poisonous. Iodine is a solid at room temperature, and it's a good disinfectant, so it's not poisonous to us, but it's quite poisonous to bacteria. And something else to know is that it's getting kind of boring at this point. They've got 7 reactive electrons, and group 7 likes to react with group 1. And so we kind of see some mirror-like properties running through group 4. 7 and 1 are very reactive, and they like to react with each other. 2 and 6 are decently reactive, and they like to react with each other. 3 and 5 are weakly reactive, and they like to react with each other. And group 4, they're poorly reactive, and they'll kind of react with anyone, you know? They're not that discriminating in general. So there's a lot of interesting properties going on here. But it's time to shake things up. The last group, the noble gases. They consist of helium, of neon, argon, krypton, xenon, and radon. Radon isn't pictured. It's very dangerous, very radioactive. And you see these often in what's quote unquote called neon signs. A neon sign only has neon in it because its atomic emission is predominantly orange. If your neon sign has any purple or blue or whatever in it, it has other noble gases that aren't neon, but we still call them neon signs in common parlance. What are the unifying features of the noble gases? They are non-toxic, so that's nice. A lot of elements are poisonous or dangerous in their pure form. They're non-toxic, they're all gaseous, nonmetals, and they have 8 electrons in the outer shell, but none of them react. They are completely unreactive, okay? I should say helium is an exception. It only has 2 electrons in its outermost shell, but it's also completely unreactive. These elements, unless in very bizarre conditions, will not react with any other elements on the periodic table. And that is why they're called the noble gases, because the chemists joked, oh, they're too good to be with anyone else. They're stuck-up nobles. They won't form compounds with anything. And that's really interesting because didn't you notice how elements that either had very few reactive electrons or a lot of reactive electrons were very reactive, but the ones with like a middling amount didn't seem to have so much reactivity? Why is that? What is so special about the number of reactive electrons and that relationship to reactivity? It has something to do with the number 8, believe it or not. Oops, sorry. The 7th group is over here. All right. I told you, again, the first group likes to react with the 7th group. 1 plus 7 equals 8. The second group likes to react with the 6th group. 2 plus 6 is 8. 3 and 5 like to react with each other. 3 plus 5 is 8. So a compound can be formed very stably when they enter basically what's called a noble gas configuration, or when 8 electrons, react together in that whole compound. It's time for the fun part of chemistry, chemical compounds. Now that we have a basic familiarity with the periodic table, we are going to start combining elements together and seeing what we get, okay? And so to remind you, the smallest building block of an element is called an atom. And when we have two or more atoms bind together, that is called a molecule, okay? And the molecule, kind of like an atom, it's going to be the the smallest particle or thing that's going to retain those bulk characteristics of that substance, okay? And some examples of molecules that you've probably heard of already is, oxygen. Okay, so oxygen, that's called a diatomic molecule because it has two atoms together. In this case, two of the same one. Dihydrogen, like hydrogen gas, tends to exist as H2, not just floating hydrogen elements. You could even get triatomic molecules like ozone, which it's actually more of like a bent configuration, but this is a close enough approximation. OOO, O3, ozone is the ozone of the ozone layer, and this helps, protect our atmosphere from certain kinds of radiation from outer space. And I personally never heard of the phrase monatomic molecule before, but I suppose I'm compelled to tell you that they exist. The noble gases like helium, neon, argon, krypton, etc. These are going to exist as just singular atoms floating about. And you'll actually come to find that if you look at the periodic table, it's pretty much only the noble gases that exist elementally, which is to say that they are not bound with something already. Iron is usually bound with other elements like iron oxide and whatever to form ores. Pretty much all the sodium on the planet does not exist as explosive chunks of sodium metal, but rather it exists as sodium chloride, table salt, like in the salt that forms the salt water in our oceans. Now, this is where the vocabulary gets a little bit nuanced, and frankly, this is not something that I think is a big deal, but there is a slight difference between what a molecule is and what a compound is. Okay, a compound is when you have two or more different elements bound together. Okay, and that would be something like H2O, water. Sodium chloride is it's a network compound. We're going to get into that in a slide or two, but NaCl, sodium chloride, two different elements. Compounds can be pretty complicated, like glucose, which is a form of sugar. It is 6 carbons, 12 hydrogens, and 6 oxygens bound together in a very specific structure, okay? And the important takeaway here is that there are multiple elements involved. You look at ozone or atmospheric oxygen, O2, O3, those are molecules, but they aren't compounds because they all have the same elements composing them. The word for a molecule that only has the same elements, these would be the word for something like these two. These are two allotropes. Okay, that's like a fun $5 word for you to know. But listen, I use molecule and compound pretty much synonymously in my work, so I'm not a big fan of semantics, but I am forced to make you aware of this fact. The $1,000,000 question of chemistry is, how do we form compounds? This is where capitalism and chemistry sort of come together, so to speak. Atoms basically are going to form attractive forces with each other using their reactive electrons. Okay, remember that term reactive electrons I was harping about when going through the periodic table? This is where they come into play. Those reactive electrons are going to combine or transfer in some way between participating atoms to form the molecules and compounds that are of use to us in day-to-day society, or just make up, our own bodies. And you can generally divide all types of chemical bonds and all types of compounds into two categories. The first would be ionic, and the second is covalent. Another word for an ionic compound is called a salt, by the way. So table salt is like the poster child of all salts, but there are many other kinds of salts that you don't sprinkle on your French fries, for example. Okay? And the differences between a salt or an ionic compound versus a covalent compound is primarily it comes down to what types of elements are binding together. So a salt is going to form between a metal and a non-metal always, okay? Another unique property to ionic compounds and salts is that the atoms are going to bear charges. And when I say that, what's going to happen, and we're going to talk about this in detail on the next slide, the non-metal is going to steal all the reactive electrons away from the metal. And so that's going to make the metal positively charged, and the abundance of negative electrons on the non-metal is going to make it negatively charged. And oh look, we have a positive charge and a negative charge. Coulomb's law. They're going to be electrostatically attracted to each other, and that charge attraction is the ionic bonds, okay? Another simple thing to know about ionic compounds, and this will make more sense once I pull up some pictures of this, is that they're going to form extended networks in a repeating pattern called crystals, okay? So table salt, if you put it under a microscope, it actually is going to look like little quartz crystals, kind of. It's going to be beautiful, and they're going to be all geometric, and that has to do with the ionic nature of the compounds. When you have positive and negative charges holding themselves together, what's going to happen is like you're not going to get a sodium chloride compound. You're going to get like positive, negative, positive, negative, positive, negative, positive, negative, positive, negative, you know, something like, I could do this all day long, but I'm not. Whatever. You get the picture. You're going to get these alternating charges, and that's going to extend indefinitely, basically until the crystal stops existing. You reach the edge of the crystal, okay? So believe it or not, like one crumb of table salt is actually one molecule or one compound, whatever you want to call it, which is kind of wild to think. But the ratio of, you know, the sodium and the chloride and sodium chloride salt is always going to be 1-to-1, okay? Regardless of which crystal you're looking at under the microscope. Okay, for covalent compounds, these are both more complicated and less complicated at the same time. The major difference between covalent and ionic is that we are only dealing with nonmetals here. These are nonmetals reacting with nonmetals only, okay? And I said when talking about the ionic compounds, how the nonmetals form their ionic bonds by stealing the metal's reactive electrons. Here in the covalent case, since the nonmetals are all pretty good electron stealers, no one's gonna completely steal one electron from one element. So they're gonna play tug of war with those electrons, and they're gonna be forced to share them. And since no one is completely gaining or completely losing electrons from each other, these compounds typically are not charged. There are exceptions, you don't have to worry about them. And as such, since we're not having charged units composing these compounds, they're not going to repeat out indefinitely in some sort of charge ratio. Okay, you're going to form discrete molecules, essentially. This is like what you would think of when you picture a cartoon of a molecule. You know, those balls and sticks, where the balls are the atoms and the sticks are the bonds between them. And they can be pretty complex, you know, like compounds can be as simple as carbon tetrachloride, which I can just draw really quickly over here in a sloppy way. And you can have something like glucose, which I mentioned before, which, oh dear, I don't even know if I can do this off memory. I won't expect you to, but glucose is going to have like, it's going to be a ring of carbon, of like 5 carbons with an oxygen. One carbon's going to be over here. That carbon's going to be bound to an oxygen. These will be bound to two hydrogens. I believe this is bound to an oxygen, hydrogen. This is bound to an oxygen, hydrogen. I think this one is actually going upwards. And, you know, I'm not even drawing the whole molecule because I'm getting sick of this. And I probably made a mistake somewhere. And this is considered a pretty simple, you know, compound still. More complex than carbon tetrachloride, but I think you can appreciate that when you share electrons, the possibilities are quite literally infinite. Now I'm going to show you how to map out an ionic compound and a covalent compound. We're going to first start with ionic because I think that's a good starting ground. And I've broken down the steps on how to approach these problems into the following four, you know, maneuvers. And I'm going to remind you that the goal to making any sort of compound for the purposes of this class is to make every atom in that compound or molecule to have 0 or 8 reactive electrons, okay? Because you may remember from when I was doing the periodic table walkthrough how I would say group 1 and group 7 like to bond together because 1 and 7 add up to 8, all right? And we're going to see an example of that with this question, is, you know, like what is the ionic compound that would form between elemental sodium and elemental chlorine? Okay, so this is how you approach this problem. First, you're going to write down the elements that were given to you in the problem, and you're going to notate them with 1 dot for every reactive electron they possess. Okay, let's do that right now. Sodium on the periodic table, and I put it here because I am not expecting you to memorize this giant monstrosity, but sodium is right over here, okay? And it is specifically in group 1. Group 1 always has 1 reactive electron to it. So I'm going to draw Na over here, and I'm going to give it a little dot, okay? And that's going to represent the 1 reactive electron that it has. Chlorine is all the way over here in group 7. 1, 2, skip all these, 3, 4, 5, 6, 7. Chlorine on its own is going to have 1, 2, 3, 4, 5, 6, 7. I think drawing these as little hashes is easier because when I scribble, PowerPoint pen gets really angry with me for some reason, which you've been suffering through the whole time, as have I. All right, so this has 7 reactive electrons. This has 1 reactive electrons. We need to get them to have 0 and 8 to form an ionic bond between this metal, blue metal, and this nonmetal, yellow nonmetal. Okay, how do we do that? The nonmetal is going to steal the metal's reactive electrons until it has a total of 8. Okay, boop. We're going to move this over here, okay? And we're going to erase this electron because it no longer has it. There we go. It wasn't letting me erase. Let me just erase these because this might be confusing. I didn't want to go that far. Okay, pretend you don't see this picture right now, okay? Because I don't feel like doing this over again. Ugh. Anyway, so sodium and chloride are going to experience electron theft by the hands of chlorine. And the reason why chlorine is the one that's stealing the electron is really just simplicity, okay? What is easier, to steal 1 or to lose 7? That is why we draw the reaction scheme out this way, okay? the end product of this electron transfer is that sodium is now going to bear a net +1 charge, and the chlorine is going to bear a net -1 charge because it gained 1 negative electron, and this lost a negative electron. Okay, so everyone now is happy. And when they're happy, they're going to combine electrostatically, and the notation for that is going to be this. You're going to draw NaCl, and you're going to put them in brackets. Oh my lord. Positive, negative, okay? And what the brackets mean, the brackets kind of imply a sense of infinity, if you will. We're saying that positive sodium ion and chloride sodium ion at this point is going to repeat indefinitely in a 1-to-1 ratio in some sort of crystal matrix. And this is a picture that I showed too early of what that looks like, with the green things are the chlorides, and then the ions, and then the purples are the sodium ions. And they alternate 1-to-1, kind of in a cube-like fashion, and that's why salt crystals look cube-shaped, okay? And that's it. It's actually deceptively simple. I think it's kind of fun that you can just form a compound with this very simple notation just by merely knowing where the metal and the nonmetal exist on the periodic table, what column they occupy. All right, now I want you to try with a slightly different question that's a little bit trickier, but I think you can certainly do it. And that question is going to be to form an ionic compound using the notation that I just described to form a salt that would consist of calcium and fluorine. And if you need help finding them on the periodic table, calcium is over here in group 2, and fluorine is just above chlorine, but still in group 7, okay? So pause the video, work at it, and then unpause so I can show you what I did, and then you can compare your results. Don't be tempted to just blaze on ahead, because a question exactly like this could very well pop up, you know, on the exam. So it behooves you to be familiar with how to do this. So I'm going to assume now that you were a good student and that you paused the video and gave it a good, honest college try. And now I'm going to model it out for you on how I would approach it. All right, so calcium, I'm going to draw it over here, Ca. That is the symbol for it. It is in group 2. That means it has 2 reactive electrons. I'll try little circles this time. Fluorine is still in group 7, and that means it's going to have 1, 2, 3, 4, 5, 6, 7 reactive electrons. Okay, step 2, have the nonmetal steal the electrons, okay? So, we are going to move 1 reactive electron over here. Fluorine minus, that calcium now has a +1 to it. Let's ask ourselves, does everyone have 0 or 8 reactive electrons? Fluorine has 8, calcium doesn't. So we need to lose another electron to allow ourselves to form a final stable compound. So we are going to add metals and nonmetals, whichever is necessary, until we have all the reactive electrons reacted. Add more metals or nonmetals. I just realized I left that part out. So let's have another fluorine. 1, 2, 3, 4, 5, 6, 7. We are going to steal this guy. And now calcium is going to have a 2+ charge. So 2 calciums, no, I'm sorry, 2 plus calcium is going to be associated with 2 minus 1 fluorines. So the final compound is going to look like this. CaF2. And you can do bracket notation as well. Honestly, I think the bracket notation is like kind of cumbersome. You need to be aware of it, but if you just drew CaF2, I'd be happy with it. But when you draw the brackets, you do need to demonstrate the charges. And so negative over there to positive over here. That subscript shows that you multiply that negative charge by 2 because there's 2 negative charges for the 2 different fluorines, and they are going to passivate the positive 2 charge. So overall, the ion is neutral, but it is the ionic compound is neutral, but it is composed of charged subcomponents. All right, and this is a picture of what it would look like as a crystal matrix. You've got, I believe, sodium here, not sodium, excuse me. Fluorine here is shown as these white spheres, and the calciums are yellow. Although in my experience, that doesn't seem quite right. In my experience, they usually like to color fluorine kind of yellowish, but I wasn't the one who made this picture. So that's all you need to know with that. The last thing to know about ionic compounds is the nomenclature for naming them, or what their naming rules are. And it's actually really simple, thankfully. All you have to do, here's like a little formula to help you memorize, is the name of the ionic compound is going to simply be the name of the metal element participating in the ionic bond plus the non-metal name, but you're going to put an "ide" at the end of the non-metal. You're going to change the word a little bit, and that's going to kind of be a signal that this is a compound, and we're not discussing elements in isolation anymore. So let's do some practice examples, okay? CSI, which is not a scientifically inaccurate police procedural show. In this case, it's an ionic compound between cesium and iodine. Cesium, iodine, okay? So the name for that is not cesium iodine, it's actually cesium iodide. That's where that "ide" comes from, that iodine, iodide, all right? And in case, like, I've got the periodic table basically memorized, I'm not expecting you to know CS and I off the bat, but just look over here. Look for where you find CS. It's a little bit of a word search, I know, but you'll get the hang of it. CS and then I. And with a little bit of chemical know-how, you can actually circumvent the deliberate one-by-one searching of where the element is with the corresponding name. Since it's a 1-to-1 ratio, we know that it is most likely going to be either a 1 and a 7 or a 2 and a 6 bound together, okay? Now over here, let's do this one next. I'll let you do the other two on your own. But we've got sodium and phosphorus. But we have 3 sodiums here that are associated for every phosphorus in this salt. Okay, the name for this is going to be sodium phosphide. Not phosphorus, but phosphide. And here's another like clue that you can use. We know that, well, maybe this clue is easy for me, but maybe it's not going to be easy for you. So I'm kind of reluctant to say it, but whatever, I'll give it a shot anyway. The 3 over here, you can kind of think of it as a clue for where the phosphorus is, because that means the phosphorus has a -3 charge. And so that would mean it would be 1, 2, 3 families from the left. So 8 minus 3 is 5. And look, there's phosphorus if you need help finding it. I was trying to be helpful, but maybe that's not so helpful. You don't have to think of it that way. If you want to be slow and deliberate and just go through one by one, just focus on these areas, and that'll make your life easier. Don't look through here. I'm not gonna quiz you on these guys, really. All right, I'll let you guys try magnesium sulfide, and oh, I just gave that one away. Well, you know that's magnesium sulfide now, and then I'll let you try this beryllium nitrogen complex next. Next up, we're going to cover the rules for covalent bonding. And to remind you, a covalent compound is one that's composed of only nonmetals. You may be wondering, what about compounds that are formed with metals and metals? They really don't exist, so don't worry about those. We're just going to focus on the covalent ones. The goal here is a little bit different for the rules for ionic compounds. Instead of doing electron theft, we want to make sure every atom is sharing electrons until each atom has a total of 8, okay? The word for, I should mention, the word for this goal of reaching 8 electrons is called the octet rule. That's a good word to know, or phrase to know. Another way of saying that is we want everything to reach noble gas configuration. That's another way of saying that, because they all have 8 outermost electrons. When you have 8 electrons, they're no longer reactive, but you get what I'm saying, okay? There's one exception to this. For compounds with hydrogen, their hydrogen is so small, it can only hold on to 2 electrons total, okay? So just be aware of that. But let's work through an example together for carbon dioxide. We're going to go through the steps together, 4 steps as well, one by one. The first step is to write down elements in the compounds and then draw, again, 1 reactive electron dot per element. So in this carbon dioxide molecule, we have C, O, and O. Okay. Oxygen has 1, 2, 3, 4, 5, 6 reactive electrons. I know this because here's oxygen, and it is in the 1, 2, skip these, 3, 4, 5, 6th row, or 6th column, excuse me. Carbon, on the other hand, is in the 4th family. So that is going to have 1, 2, 3, 4. Okay? This oxygen is chemically identical to that oxygen, so it's going to have 1, 2, 3, 4, 5, 6 reactive electrons as well. All right, so we did this step. This is the quote-unquote hard part. We are going to pair elements with covalent bonds. And a covalent bond is merely a pair of electrons that are shared between both atoms that are being linked together. These electrons, you can think of it as existing as both atoms in it, okay? So what we're going to do is we're going to marry off some of these electrons. We're going to take 1 electron from here, oops, 1 electron from oxygen, 1 electron to carbon, and we're going to marry them, all right? Like that, and we're going to do it like that, okay? So let's draw it like this. Oxygen, electron, electron, carbon, and this has 1, 2, 3, 4, 5 left over. And this oxygen is the same thing. This electron came from that carbon. This electron came from that oxygen. Oxygen has 5 electrons left over. And, oh, we can't forget these guys, okay? Always make sure you do your accounting well. Carbon had 2 other electrons in it, okay? So now we're going to do step 3. Make sure each element bears 8 electrons, or 2 for hydrogen, okay? So let's count up the ones with carbon. We have 1, 2, 3, 4, 5, 6 electrons associated with that carbon. No bueno. These oxygens are also going to be no bueno. 1, 2, 3, 4, 5, 6, 7. And the same for this. We are failing the octet rule currently. Okay? So we got to fix this. How do we do that? Well, you can make single, double, and triple bonds. Okay? And a single, double, triple bond will consist of 1 pair of electrons, 2 pairs of electrons, or 3 pairs of electrons. Okay? So we're going to modify this. We're going to give this another go, and we're going to make an additional bond between these atoms. This one, this one, and this one will come together, and this one, and this one. And it doesn't matter which electron I'm picking. Like, I can have it bond with that electron or that electron. It doesn't really matter, okay? Because technically, the positions of the electrons are uncertain according to the laws of physics. All that matters is that we are pairing off another set for a total of 2 double bonds. So to draw that another way, I'm going to do OCO. I'm going to do a line instead because I hate drawing these little dots, but each line is considered 2 electrons, remember, okay? And we took 1 electron from the 5 remaining on each oxygen atom, so now there's 1, 2, 3, 4. 1, 2, 3, 4. And now let's go back to step 3 and make sure that we all have 8 on each atom. 1, 2, 3, 4, 5, 6, 7, 8 electrons associated with oxygen. All right? For carbon, remember these are covalent bonds. That means they share the electrons. These 4 electrons belong to oxygen. They also belong to the carbon. 1, 2, 3, 4, and don't forget these, this double bond over here, 5, 6, 7, 8. So oxygen has 8, carbon has 8. And this oxygen-carbon bond is identical to this one, so we don't even need to count, and we can know that this satisfies the octet rule, okay? So if you like drawing pictures, I think, you can have a fun time with this. But for the first time, I understand this may be kind of complex compared with, my shaky handwriting. So by all means, if you feel a little bit shaky about this, don't hesitate to rewind, a few minutes and just watch me go through this process again before you get to practice on the next slide. And as I promised, you are now going to work on this problem completely on your own. I am not going to give you the answer. You'll have to double check that yourself. Use that through Google, or you can simply ask me during office hours or in the middle of lab. But I want you to draw the dot structure for a water molecule. And that consists of, I'll remind you, of oxygen in red and 2 hydrogens, H2O. And I'll also remind you that the octet rule for the hydrogen atom is going to be a little different. It can only have 2 electrons affiliated with it at any given time. So I'm just going to blaze on ahead, but you pause the video and work it out for yourself because this is a good skill to have for the test. Now we're going to discuss the naming rules for covalent compounds, which are a bit more complicated than for ionic compounds. For ionic compounds, you may recall that you only need the metal plus non-metal iode, okay? And remember that example of sodium phosphide. It had 3 sodiums in it, and there was no need to specify that there were 3 sodiums in the name because it will always be 3 sodiums to 1 phosphorus, okay? generally speaking. For covalent compounds, that's not necessarily the case. You can't predict the ratio of one element to another based off the ions they form because we're not forming ions here, okay? It's all covalent and it can be very ambiguous. So we need to be more descriptive as a result. And to be more descriptive, this is the convention that we use to name covalent compounds. We have the name being formed as a prefix with the first nonmetal listed, plus the prefix with the second nonmetal listed, and we're also going to add that "-ide" suffix at the end to denote that we are dealing with a compound here, that these elements have reacted together, okay? And the prefixes are going to be used to tell you how much of that element is in that compound as denoted by the subscript in its chemical notation. So in this example, we have N2S2, nitrogen and sulfur, 2 nitrogens and 2 sulfurs, so it's dinitrogen, disulfide, okay? And here's like a little table to help you find out if you don't know Latin and Greek that well. If you have one of something, it's mono, 2 di, 3 tri, 4 tetra, penta, think pentagon, hexagon, you know the drill. Just to be comprehensive, I should probably also mention that 9 is nona. You don't see a lot of compounds with 9 of one atom in it, though. You occasionally see some stuff with 10, and that would be deca. So, just so you know. Okay, now, covalent naming compound rules can be a little annoying because there's a lot of exceptions to them, all right? And they're kind of arbitrary, but you have this slide to reference to, so you'll never have to memorize it, but you'll have this as a useful cheat sheet. The first exception I will discuss is mono. You drop the mono for the first elements, usually. I would say always, actually, not just usually. We don't call it monocarbon dioxide, we call it carbon dioxide. And that's just because so many things, so many compounds have just one thing in the beginning, and it can be verbose, wordy, annoying to just constantly say mono this, mono that. It's laziness. The second exception is purely cosmetic. For the prefix of the second nonmetal, drop the vowel to avoid awkward AO or OO combinations. What do I mean by that? Carbon monoxide just sounds better than carbon monoxide. It's just weird, okay? Where things kind of get a little tricky is certain vowel combinations are someone decided that they are not as ugly and they are therefore tolerable. I think it has something to do with you want to avoid changing what the element sounds like at the expense of this nomenclature. In this compound, Bi3, which is boron triiodide, you don't want to call it triodide because that sounds like it came from the element triodine, and which is not a thing. So you don't want to say triodide. You want to say triiodide, even though the double I looks weird. Deal with it. The third exception, and this is the easiest one to wrap your mind around, is that common names take precedence, okay? H2O, we all know that's water. Don't call it dihydrogen monoxide. One of the reasons against that is anything that ends with monoxide usually sounds dangerous. Carbon monoxide being the poster child for that. And I suppose a lot of monoxides are, I guess. So we just call that water. Ammonia is another compound you may be familiar with. Don't call it nitrogen trihydride. Everyone just calls it ammonia because that's what it was first. It was named ammonia first before, these chemistry nomenclature rules were established, okay? What did I want to say next? Oh yeah, a fun thing about dihydrogen monoxide is it's a very common societal experiment, I guess you could say, where people will go on the streets and they'll say, "Oh, we need to ban dihydrogen monoxide. It's present in our rivers. It's an industrial solvent. It's found in the lungs of drowning victims. It's present in practically every dead body, a freshly dead body." It's a fun little experiment to show, I guess, chemical illiteracy, scientific illiteracy. You know, just because something has a scary chemical name doesn't necessarily mean it is a scary chemical, okay? Chemicals are neither good nor bad, it just depends on their application. And water is just one of many chemicals. And I'll get off my soapbox. It's worth repeating because I mentioned it briefly on the previous slide, and this is a subtle note, that why is it that the naming rules for covalent compounds are so much more complex than ionic compounds? Well, the bonding ratios of an ionic compound, I'll repeat for you, they're solely dictated by the charges of the ions that form from them. The ratio of sodium to chloride in sodium chloride salt is always going to be 1 to 1 because the charge on the sodium ion will always be +1 and the charge on the chloride will always be -1, okay? And so that's how they're going to pair off and be neutral. But when we share electrons covalently instead of stealing them ionically, we can combine elements in numerous ways, okay? Let's take nitrogen and oxygen as an example. Here is just a subset of the many compounds that you can make with these elements. Nitric oxide, for example, NO, this is an industrial precursor to a lot of materials. I believe a lot of plastics are nitrosylated, for example. I think acrylics in particular. Nitric oxide is also a biological molecule. The human body can make nitric oxide, small quantities in our bloodstream. It is a biological messenger that has many roles, one of which is to stimulate blood flow. That's actually how Viagra works. Viagra, which I think the brand name is, or the technical name is sildenafil, it is a compound that will stimulate an enzyme in the human body to overproduce nitric oxide. And that will increase blood flow to certain areas as deemed desirable by the person who takes it. Okay? Very interesting stuff, though. Dinitrogen oxide, N2O, that is a brownish pollutant gas and a greenhouse gas. It's a little poisonous, and it's the reason why that brown smog haze exists sort of over the horizon. It is a byproduct of a lot of industrial processes, okay? Nitrogen dioxide, also known as nitrous oxide, that is an anesthetic. It's also known as laughing gas, okay? So it's biologically active, it's a neural suppressant because of it makes you loopy nature, and it's also used as a propellant in pressurized canisters like that of whipped cream. That's why certain drug addicts, known as huffers, or who prefer inhalants, they can sometimes sniff the NO2 out of the whipped cream can. But I highly recommend against it. All drug use is usually bad. And that was actually, what's his name? Aaron Carter, I think, was really into inhalants. And in addition to slowly killing your brain, he, I think, did that in the bathtub, and it knocked him unconscious, and then he fell in and drowned. So don't do drugs, kids. These last three nitrogen-oxygen compounds, dinitrogen tetroxide, dinitrogen pentoxide, and trinitramide, these are all powerful oxidizers, which makes them good rocket fuels, actually. And this is interesting. Trinitramide, which is shown over here, it was actually only discovered in 2010. And it's really impressive to think that a molecule as simple looking as N4O6 was discovered less than 15 years ago. I mean, it has 10 atoms in it, right? A plastic compound, by comparison, is huge. One plastic compound can have millions of atoms in just one of those plastic molecules. And so, why did it take so long for us to discover a compound that only has 10 in it? That's really where the beauty of chemistry comes into play. If you mix a bottle of nitrogen and a bottle of oxygen together, how do you convince it to form, this compound over that, or this and this compound and none of that compound, and etc. Finding the exact ratios of those two gases, the temperatures that you react them in, the pressure of the gas that you cram into the reaction vessel, and how long you sit it there and react, all of those factors are tunable and allow you to make, one compound over the other. Finding those exact conditions is one of the evergreen questions of chemistry. How do I set up my reagents? How do I build a recipe to get the products that I want? And that is the question that we will begin to answer for our next lecture.